welcome back. Here we're going to deal with the normal distribution again, but here we're going to talk about finding percentiles. And so pretty much what these are, they're the inverse of probability. So in all the other previous questions, I gave you a number and you had to find the probability associated with that number. So what a percentile is, percentile, think about it as 90%, 80%, 10%, 5th percentile. So what in these problems, what they do is they give you the probability, and now you got to find the number such that it will give you that probability. So we're working backwards here. Okay, so it says we are given the probability and we have to find the outcome such that the area to the left is equal to the probability. Okay, so this is called the percentile. Okay, so here what we have here is a distribution of fish lengths. Okay, they're in inches. What we're saying is that if we were to record a bunch of fish lengths and create a histogram, we would model it using a normal curve. So the average fish length is 16 inches, the standard deviation is 4. So of course the center of this distribution is at the mean, 16. And of course we have 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. Okay, so here we get more or less the gist as far as the typical lengths for the fish we should expect to see, and of course we kind of get what's kind of what's maybe not so typical fish lengths to see. So in this example, they're saying they want us to find the 10th percentile. Okay, so here we're saying probability. So if they want us to find the 10th percentile of fish lengths, what that means is finding the fish length such that it's going to be larger than 10% of the fish, of the other fish lengths, and pretty much the remaining 90% fish lengths are going to be larger than it. Okay, so maybe by saying 10th percentile, right, we're trying to find this region here, meaning like the really small lengths of fish for this study here. Okay, so what it comes down to is we want to find the x, right, the fish length, such that the area to the left of it, and so this is like a less than or equal to, right, is going to be equal to 0.10. Okay, 0.10. So if I were to do this in StatCrunch, we're going to use the same calculator here. Okay, so we say fish lengths follow a normal distribution, mean 16 inches, standard deviation 4 inches. We want to find the 10th percentile of fish lengths. Okay, so we can plug this into the normal calculator, but order matters here. So before I plugged in for x and I would get out the probability. Now we're going to plug in the probability and get out the x. So let me just show you how I do this in StatCrunch to make sure that I get the order right here. Okay, so if I click on StatCrunch here and I open StatCrunch and I go to stat and I go to calculators and I go to normal. Okay, so here the mean is let me make this a little larger here. The mean here is 16, and the standard deviation is 4. Okay, and so I don't really know what this value is. I don't know what that is, but I want to find the number here such that the area being less than or equal to it is 0.10. Okay, so that's why I'm saying the order matters here. In the previous example, we plugged in a number here first and then we got out a probability. Okay, and so now what we're going to do is here is plug in the number. We're going to compute now. Okay, so when I compute, see the numbers here now. So here it found the number such that the area to the left is equal to 10%. Okay, and roughly this number here, the 10th percentile fish lengths, is roughly 10.87 inches. Okay, 10.87 inches. Okay, that is the 10th percentile of fish lengths, meaning that 10% of fish lengths are going to fall below 10.87 inches, but also implies that 90% of the fish lengths are going to be greater than this amount. Okay, so that's what we're doing. We're finding the probability, find me the number here. Okay, so as far as using the table, right? If we're using the table to find the percentile, well, we're still going to use the z-score. Okay, I'm gonna say, but the thing is, I don't know what k is, right? I don't know what this amount is. This k is the 10th percentile, but I know I can set my z-score equal to the 10th percentile, and of course I subtract the mean divided by standard deviation. Remember, this is just equation of the z-score. So what I do here is I look at the z-table. Okay, look at the z-table, and I say, well, what's the 10th percentile? Looking at the standard normal table. Sometimes they call it the Z table because Z always means normal 0, 1, okay? But here I go, what I do is I look up in the standard normal table, okay? I'm looking for, because this is 10th percentile, so like 10%, so in decimal, it's 0.10, okay, 0.10. So in the table, I'm gonna look for the probability that's closest to 0.10, and then reverse battleship to get this number here, okay, the z-score. So negative 1.28 is the 10th percentile of a standard normal distribution, okay, where the mean is 0, standard deviation is 1. So what I do now is I plug this negative 1.28 into here, and then I just have an equation where I need to solve for k, okay? So if I solve for k, I multiply by 4 on both sides, add on 16 on both sides, I will roughly get 10.88 inches is the 10th percentile. All right, so very, very close to what we got in the previous one without using the technology. And if you look here, how I did it, so remember 10th percentile, 10% in decimal is 0.10. So I'm looking at all of these probabilities. I'm looking in here first, okay? When I was finding probability, I looked at the z-scores, but now I'm looking here first for percentile. Okay, so I'm looking for percentile. What's closest, right? This is 0.08, 0.0823, 0.0985. That's 0.1026, 0.1003. This probability here is the closest to 0.10. Okay, so in that case, this is, I'm going to find the z-score corresponding to this 0.10. So that's where I go reverse battleship. So here I get negative 1.2. And up here, I get 0.08. So that's where I get my negative 1.28. So remember, I just put this together with this, and that gives me my total z-score there. Okay, negative 1.28. Okay, so that's what gives me. That's how I found the z-score here. Okay. All right. So just in general, I mean, we've kind of have done this already. Right, we're looking at histograms, and we're saying based off the histogram, does it appear to be unimodal and symmetric and no outliers? Because if it's unimodal and symmetric, then we can rely on the mean and the standard deviation, right, to help us measure the center and the spread around the center. And we can also use the empirical rule and saying 68, 95, 99% for data. Right? And so now we're taking it a step further. We're saying, well, if this appears to be unimodal and symmetric, we can assume that this data, that the phenomenon, we can model this phenomenon using a normal curve. So that's what's in red here. That's what's in red here. So these distributions appear to be, more or less symmetric. Right? This one has a little skew into it, a little bit of skew, but still you see the model fits very well. So the red is the normal, and the blue is just like what the data is, like the shape of the data. You see these blue and red lines look very similar. The histograms and the red line look very similar. Now down here, obviously we have something that's multimodal here, right? Multimodal. So in this case, we definitely don't want to use the normal distribution. We don't want to use the normal distribution, or if we're talking about measures of center, we're definitely not going to use the mean or the median in this case, because we have more than one mode, right? When we have more than one mode, we definitely need just different techniques that are beyond the scope of this class. Okay, and then of course here it appears to be maybe we have two modes here. Maybe slight skews, kind of hard to tell, but maybe these models aren't appropriate. But really, when we're looking at these histograms, looking for unimodal and symmetric and no outliers, we're kind of looking for, can we model this with the normal curve? Okay, the normal curve. So so that's what we get right there. Okay. So, and then of course here, if we're talking about poker earnings, right, we're talking about gambling the other day. And so, I mean, most of our win or loss amounts are around zero. A lot of times we're going to lose some money, and sometimes we might win some, and every once in a while we're going to hit the jackpot, right? We're going to hit the jackpot. But, if we want to model like poker earnings amongst various gamblers, a normal distribution definitely wouldn't be a good fit here due to the fact that someone can win the jackpot. It very rarely happens, but it does, and we should include these in our study. So we need a different kind of curve to model something like that. Okay. So what I want to get into here is the last section in chapter 6, which is the binomial model. So I just want to introduce the binomial model, and we've seen it before in simulation when we're counting if we're doing the kissing the right way study, right? The number of times a couple tilts their head to the right when they're leaning for a kiss. If we're counting the number of leans to the right over 20 couples, that follows the binomial model. And so here we say here the binomial model. So remember, normal was a continuous model, but the binomial is discrete variable, okay, which counts the number of successes out of n trials, right? So we're counting the number of tilting head to the right out of 20 kisses, let's say. So the binomial criteria here is that the procedure has a fixed number of trials. Okay, so when we observed the 20 couples, that number was fixed, right? We didn't increase it or decrease it due to some circumstance. The trials must be independent. So within kissing the right way, like each couple's decision to tilt their heads to the left or the right, they're independent of each other. Okay, each trial have all outcomes classified into exactly 2 categories. So what we're saying there is that either you tilt your head to the left or to the right, and in general we call it success and failure, right? And the successes are what we're counting, right? And then part 4, we're saying the probability of success remains the same in all trials. So here we're just saying in terms of the couple, they all more or less have the same chance of tilting their head to the right or to the left, right? Or if we're flipping a coin 4 times and counting the number of heads, well, my number of coin flips is fixed. Each outcome of the coin flip, they're all independent of each other. And each outcome, it's either heads or tails, and the probability of heads remains the same on each trial. Okay, so these are kind of the requirements needed to use a binomial model. Okay, and really quick, some of them have equations here, and I don't want to scare you too much with this equation, but what this thing is doing here, that's called it counts combinations for us, and these exclamations are called factorials. So what this will do for us, it'll automatically count the number of ways you can get X number of heads out of n total trials. Okay, so say we want to count the number of ways to get 10 heads out of 1,000 trials. Well, this will automatically count it for us. So in class we did an example where we're flipping a coin 4 times, right? And we had 16 total outcomes, and the number of ways in which we got 1 head, there was 4 ways in which we got 1 head, right? So but we had to count them by hand, but what this thing does is it counts for us. Okay, but anyways, we have number of trials, number of successes, probability of success, probability of failure, which is a complement. Okay, so we'll minus that. And then of course here, the mean of the binomial is number of trials times the probability of success. And the standard deviation of the binomial is the square root of the product of number of trials, the probability of success, and the probability of failure here, right? So this should make sense because say we have a fair coin, 50-50 chance. If we flip it 10 times, how many heads would you expect to see? Well, 5, right? About 5 out of the 10. So how do we do that? Well, we're doing 10 times a half, which would be 5, okay? And one thing to note about this binomial distribution as far as its shape, it could be symmetric, right? Kind of look like a normal curve, but it can also be skewed. Okay, so the probability of success is very small, it's going to be skewed to the right, and if the probability of success is very large, it's going to be skewed to the left. Okay, so this distribution takes on the normal distribution that we saw before. It's always symmetric, it's always unimodal, right? But for this binomial, well, it depends. It could be symmetric unimodal, but in other cases, it was going to be unimodal skewed right or unimodal skewed left. Okay. So just to look at some examples here, we say number of heads out of 20 coin flips. Is that a binomial model? Well, we could say yes, it is, right? So the number of trials is fixed. Outcome of each coin flip is independent. The probability of heads is the same for every coin flip. And there's only 2 outcomes per trial, either heads or tails, right? Number of phone calls received per week. Well, the reason that's not binomial is that, well, maybe each incoming phone call, they're independent, but what's not fixed is the total number of phone calls you can receive per week. Okay, some can receive 100 phone calls, some can receive 10, some can receive 0, some can receive 5, but this total number, right, the total number of trials is not fixed in this case here. Here, number of students in the class that completed homework, right, that would be a binomial model. So I'm just saying each student's outcome, they're independent from each other. There's only 2 outcomes, either they completed the homework or they didn't. And each, there's a fixed number of students in the class, okay, 39, and so on and so forth there, okay. If I did this, number of three-pointers made until first miss, well, that's definitely not. And the reason is that, well, if we're, say I shoot, I make a 3, I shoot, I make a 3, I'm going to shoot until I miss. Okay, so it's kind of like flipping a coin until you see your first tails. So the total number of three-pointers shot, we're not going, it's not a fixed quantity, right? So really what we're saying here is that we're counting, so I shoot, it's either miss or make, shoot, miss or make, shoot, miss or make. All right, so maybe each, they're independent. Each shot has the same chance of making the 3-pointer, but we don't have a fixed number of trials here. Okay, I can miss on the first one and then I'm done. All right, or I can miss on the second one and then I'm done. So one has 1 trials, one has 2. Here, the number of games the Lakers win over a month. Well, that's that's all of them, right? I mean, we don't even need anything here. But I mean, really, the reason this wouldn't work, the number of games would be fixed. Okay, so we don't have to worry about that. But the probability of success, the probability of winning, would that be the same for every game? And so the question would most likely be no, because of the games that are home versus the games that are away. Typically, teams have a much higher win percentage at home than they do when they're away. So the probability of success is not the same for each trial, right? Or if you were to be flipping a coin, the probability of heads will not always be 50%, is what we're saying there. Okay. So anyways, so just to give you an example here of a binomial experiment. So we're not gonna worry about that that equation that I showed you before, okay? But we can work with smaller ones like we did already when we were flipping a fair coin 4 times. So when we flip a fair coin 3 times, what are all the outcomes that can occur? Well, there's 8 different outcomes here, okay? 8 different outcomes. So, all heads, here I get 2 heads, here I get 2 heads, and here I get 2 heads. Here I get 1 heads, here I get 1 heads, here I get 1 heads, here I get all tails, okay, or no heads. Okay, so now what I'm doing here is X is the number of heads out of each coin flip. So this is a fair coin, so the probability of each one, right? So if I want a probability of heads and heads and heads, that's a half times a half times a half, which would give us 1/8, right? Since it's a fair coin, right, each of these outcomes is equally likely to occur, right? So here, so for 0 heads, there's only one way for that to happen: tails, tails, tails. So 1 out of 8. Now 1 heads, how many different ways can I get 1 heads? Well, I get 1 heads here, I get 1 heads here, I get 1 heads here. So there are 3 ways to get 1 head, so 3 over 8. Okay, that's the probability of getting 1 heads. Okay, now for 2 heads, how many ways can I get 2 heads? Well, here, heads, heads, tails. Here, heads, tails, heads. And here, tails, heads, heads. All right, so I get 3 scenarios where I get 2 heads. Okay, and then here, there's 1 case where I get, here, this is 3 heads, right? And there's only 1 way I can get all 3 heads. Okay, here. All right, so pretty much what we're doing here is this 3 over 8 essentially what we're doing is counting the number of ways in which we can get one head out of 3 coin flips. So what we're saying is that, like, this is coin 1, coin 2, coin 3 results. So we're saying that this 1 heads, it can appear at coin 1, at coin 2, or coin 3. And that's what we get here, because this is heads, tails, tails. So we got heads in the first coin flip. This is tails, heads, tails. So we get heads in the second coin flip. And this is tails, tails, heads. So we got the heads in the third coin flip. Right? So if we go back to that formula with the factorials and the exclamation marks, what that does is it automatically counts all of these for us, right? But for a small sample space, we can do this on our own, counting here. Okay, so really quickly, what if the coin is not fair? Okay, what if we have an unfair coin? Can we do the same, just count the number of outcomes and put them over 8? And the answer is no. Okay, because here, what I'm saying is, so same setup as before, the coin is flipped 3 times, results are independent, the probability of success or heads is 80% every time, okay, but what happens is now that the coin's not fair, right? So if I want to do probability of 0 heads, that means that I get all tails, 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 tails. So probability of tails is, and all these are independent, so probability of tails is 20% times 20% times 20%. But I just wrote it in fraction. 1/5 times 1/5 times 1/5. That gives me 1 over 1/25. Right, so definitely getting all tails here is much, much less likely than getting all tails if it's a fair coin, right? Because if a fair coin is 1/8, now it's 1/125th, right? So it definitely dropped, right? Now here, what we want to do is we want to find the probability of getting 1 heads, right? So if it's 1 heads, then I get, 80% times 20% times 20%, right? Or 20% times 80% times 20%, or 20, 20, 80, right? But really when you multiply, it doesn't matter which order you do it, right? You're still going to get the same number. So here I'm just doing, 20% times 20% times 80%. Right, and then that quantity, I'm just multiplying it by 3, because there's 3 ways that I can get 1 head out of the 3 coin flips. So if I just multiply these, 3 times 4, that's 12 over 125, so 12 over 125. Okay, and we do the same here. There's 3 ways we can get 2 heads out of 1 coin flip, but see, the probability jumps up a lot more. Okay, in the previous slide, when it was a fair coin, probability of 1 and 2 heads are exactly the same. But now that's unfair and actually favoring heads a lot more, you're much more likely to observe 2 heads out of 3 coin flips than 1 heads out of 3 coin flips. Okay, and then finally, the chances of getting 3 heads, well, this is heads, 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 which is 80% times 80% times 80%. Okay, which we just write in fraction, 4/5 times 4/5 times 4/5, and this is actually the most likely occurrence here. So if you see here, I mean, this distribution would be skewed. We have a spike at 3 and it'd be skewed to the left, and as you go to 0, the frequencies become smaller and smaller and smaller. Okay. So the next example, we'll be dealing with the binomial distribution with a larger number of trials, where there's no way we're going to make a table because there's just way too many outcomes. So, but we'll save that for the next video.